Welcome back to Computer Science 50, the end of week 0. Why don't we begin, perhaps with a bit of awkward silence? I need a volunteer. I see a hand and some fingers pointing at this gentleman here. So come on up. You have to be comfortable, of course, appearing here on film. So the teaching fellows are going to get your signature afterward. But come on over here. We're going to introduce today, by way of this little program, Oscar Time, which just happens to be one of the first Scratch programs that I wrote when I was first introduced to this environment over at MIT a couple of years ago. The instructions will momentarily appear on screen. It's about a minute or so of animation here, and we'll see just how high of score that you can get. What is your name?
Daniel.
Daniel. All right, so good luck to Daniel. Go ahead and click the green flag in the top corner.
Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because it's trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Here's some more rotten stuff. I have here some newspaper, 13 months old. I brought this inside and it's smelly and old. But I wouldn't trade it for a big pot of gold. I love it because it's trash. Yes, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten.
Oh, big finale coming up.
Yes, I love trash. Now look at this restless junk. I have a clock that won't work and then no telephone. A broken umbrella, a rusty trombone. And I am delighted to go. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash.
All right. Congratulations to Daniel. You could just fill this out for. So the first takeaway here should be, when you're designing your Scratch programs, don't choose a song that's a minute and a half long. Certainly not something you want to listen to for 6 hours on a Friday night while implementing this thing on loop. So we're actually going to use Oscar Time for the sake of deconstruction today when we look at a few of the more sophisticated features of Scratch. And again, it's meant to be a teaser as to the types of programs that we hope some of you will ultimately submit for problem set 0. Today's first and only handout is this one. It's essentially a summary of the first round of sections, super section, and office hours that are coming up. As this document says, do double check the website before showing up at anything, just in case we have to move a time or a day or a person or a room around. Know that the first round of sections are open sections. Just pick any day and time and show up with any of your friends, perhaps. And it's in next week's sections that will actually assign you. So per problem set 0, you are asked to section for the course between next Tuesday and next Friday online via the URL provided. The first super section will be this coming Wednesday in Science Center B. This, again, is meant to be as a supplement to those sections. So if you're finding, especially early on in the semester, even though we're playing around with Scratch currently, that you have some questions you want answered, and maybe you want to ask the teaching fellows how you can actually actualize the vision you have for your Scratch program, the super section is meant to supplement your own sections. And then finally, of course, we have office hours, which will become a staple of this course in the basement of the Science Center. These are opportunities really for one-on-one hands-on assistance. And those virtual office hours that we introduced verbally on Monday will begin with problem set 1. Before we proceed, any questions today? Okay, do just catch me after class if you need any signatures for pass, fail, or the like. And let's go ahead and take a look at the following. So we concluded on Wednesday with the end of sort of the most basic features of this programming environment known as Scratch. And again, the point of all of that wasn't so much to teach you Scratch, was just to introduce, though, in a sort of gentle manner, some of these basic fundamental constructs that will be laced throughout not only this course, but programming itself in general. Among those constructs were things like loops and conditions and Boolean expressions. Well, we concluded on a note about threads. So in just sort of an English sentence, what is a computer thread with respect to a program? Anyone at all? Yeah. Yeah, so it allows you to run multiple things at once. Well, what does that mean in the context of Scratch? Well, as soon as we started seeing Scratch programs that had multiple sprites or individual sprites that had multiple scripts, they were able to do multiple things in parallel because Scratch itself supports multiple, quote unquote, threads of execution, to be even more technical. And all that means is that the program can do or create the appearance of doing multiple things at once. But the caution that we put forth on Wednesday was that a computer can't really do, most computers, more than one thing at a time. Why is that? At the end of the day, what piece of hardware is in charge of what a computer is doing? Yeah, so the processor, aka CPU. Most computers these days, though this is beginning to change, have just one CPU inside of them. And it's damn fast, 1 gigahertz, 2 gigahertz, and it can do millions of things per second. But it can only do one thing per any given unit of time. And so what you have these days are operating systems like Windows and Mac OS that create the illusion, for the sake of the user's experience, that that CPU is actually doing multiple things at a time, when really all it's doing is tiny fragments of multiple things at any given time and just oscillating among them. It wasn't too long ago when computer software, say old versions of Microsoft Word, if you had a 5-10-page essay, back when I was in middle school and high school and was typing up my essays this way, and it came time to print out, say, a draft of your essay, well, you would go to File, Print, hit Enter, and then you would have to wait. You would wait a minute, 5 minutes, longer, depending on how long the essay was, before you could actually continue using Microsoft Word, because up on your screen during that 5 to 10 minute period of time for long essays was what kind of message? Sending, spooling, or maybe just more simply, printing, ... And back in the day, most programs just weren't multi-threaded. They could only do one thing at a time. So if you wanted to print, they'll print. But that's all you're going to be able to do. And certainly nowadays, we take for granted the fact that just by hitting Alt-Tab or just by resuming our work, we can, in fact, do multiple things at a time. But it's because, usually, that the underlying software or operating system or computer itself is providing us with this idea of multiple threads. So we saw this most clearly with this example. What did this program, when executed last week, do for us? All right, so the cat chased the bird, right? And as soon as the cat touched the bird, the program ended. But all of this was happening in lockstep. But in reality, it was sort of like, and it was happening too fast to really notice this, the bird would move a pixel, the cat would move a pixel, the bird would move a pixel. And so it looked, in the aggregate, like everything was happening at once. But in reality, it wasn't. And we'll consider toward the end of today some of the implications of this sort of parallelism, this threading, because you actually run into fairly sophisticated problems when a computer can actually be doing multiple things at a time. And we'll look at that briefly in the context of Oscar time. So this one, just as recall, when we played this thing, that was just another example of a program that did what? Who recalls? Even if you don't recall, you can pretty much infer it from these programs themselves. What did it do when run? Good, right? Or rather, you start the program and the thing starts meowing ad infinitum every couple of seconds. But once you hit the space bar, the thing stops meowing. And you hit it again, it starts meowing again. All right, so silly little example. But what's really the point? Well, the takeaway from little examples like these are that even if you have just one sprite, one program, but that has multiple threads, hopefully there's some way for those threads, so to speak, to intercommunicate so that one can be dependent on the other, or one's actions can influence the behavior of another. In this case, we've taken the approach of having one thread handle the process of figuring out if, in fact, the key has been pressed. Well, what, in a sentence, does the right-hand script do if it detects while checking forever that the spacebar has been pressed. So it changes this variable, which I just happen to call muted, just so that it's sort of self-explanatory. It's a Boolean variable in this context. What does Boolean tend to mean again? It's just true or false, 0 or 1. So I just arbitrarily said, well, if the person hits the spacebar and that variable is currently set to 0, aka false, we'll toggle it, so to speak, and make it true. Well, rather, if the spacebar is pressed but muted is not 0 but something else, presumably 1 by inference, then go ahead and change it to 0. And then go ahead and repeat and just keep waiting for the user again and again. But meanwhile, notice what the left-hand script is constantly doing. What's it doing? So it is playing the sound unless it's muted. All right, unless that variable specifically is set to false, aka 0. So this is a simple example of this inter-thread communication, but what it captures is the idea of shared memory, as we'll begin to call it. So there's clearly this variable called muted, and it's global in some sense. It's not local to just one of the scripts, but rather it's global in the sense that multiple scripts can affect its value and can check its value. So this is sort of an instance of your capability within Scratch of allowing your own scripts to intercommunicate, in this case, in a fairly simple way. I need another awkward silence and another volunteer. All right, come on down. What's your name? Lauren, you look a little too excited to do punch out here, but that's OK. So I'm going to go ahead and open what's called david.sb. Again, I have to give credit to a grad student at MIT who actually put this together. I simply removed his face and added mine. And let's go ahead and see how this thing works. There are no instructions on the screen, but it works simply by hitting the up arrow key and the down arrow key. And there is a climax once you've hit the guy enough times. Congrats to Lauren. Thank you. Here you go. We need your signature there. All right. So we won't spend too much time on this particular example. And actually, let me go ahead and hide the source code again. But just based on what you know now of this environment, how it works in terms of scripts and sprites, how do you think this thing is implemented? Just start calling out, just sort of guess how certain aspects here are implemented, if that's not too vague a question. Say anything that might be accurate about this program. Yes? OK. Sure. So just to summarize, there probably is some kind of variable, maybe that's initialized to 0. And then every time one of the gloves makes contact with my face, it increments that variable, +1, +1. So it just keeps counting up and up and up. And it does turn out that Scratch has this ability by way of just like a color wheel to say, make this color number 1, make this color number 2. And so that's how the TA, or the graduate student, sort of made this gradient of color changes. But presumably, there's also hard-coded into this program some kind of terminus. Like if that variable's value equals 20 or 30, however many times it took Lauren to actually knock me out, well, as soon as the variable hits that value, well, what clearly was the program designed to do? Sort of knock me out and rotate that sprite's costume, as it's called, 90 degrees, and then say I got pwned. All right, for the uneducated of you, you can Google what pwned means these days. It's geek speak, really. All right, so how many sprites do you think are involved in this program? Yeah, so at least 3, and maybe there's some stuff going on behind the scenes, but that seems reasonable because the gloves seem to be independently controlled. You hit up, one punches, you hit down, the other punches. My face is presumably its own sprite. In the background, you see obviously the sketch of like a boxing ring. That's probably implemented either by a sprite or what Scratch calls the stage area. You can actually slap costumes, so to speak, on the stage area. But odds are that's exactly what this program boils down to. And in fact, we can see at the top that that variable that we'd be making inference about is in fact called score, and it looks like that terminus value is just 16. Hit me 16 times, and I do apparently fall down. All right, well, let's take a look at one final, perhaps more sophisticated feature, not just of Scratch again, but of programming in general. And realize that these kinds of topics, threads and events, typically we're not able to get to in an introductory class because the means by which you implement these ideas in traditional languages like C tend to require more than, say, just 4 months of experience in programming. And so that, too, is sort of the nice aspect of Scratch, even though, again, and I know I presented this perhaps with a poor choice of words the other day, it was designed for children. It was designed for children by computer scientists, by well-versed programmers. And so what it does capture is many fundamental constructs of programming, some of which we'll continue to use throughout this course, some of which some of you won't see again, say, to Computer Science 51, Computer Science 161, or other courses. So there's this other capability in a lot of programming languages called event handling, where you can have sort of inter-program or inter-thread communication, not by just changing the values of variables, but by, quote unquote, throwing an event or triggering an event. And that means that one sprite in this case can sort of trigger an event and broadcast to the world some kind of message, and other sprites in this context can be programmed to listen for those events. Those sprites don't know when those events are going to get thrown or triggered, but as soon as they do, they'll begin operating. So this is a very simple manifestation of exactly that idea. This Marco example works essentially as follows. If I open marco.sb, and again, all of these files are available on the course's website if you want to tweak them and play around with them at some point. In Marco, we have the following demonstration. I hit the space bar, Marco says Marco, and the girl responds with Polo. All right, so a very boring program. And you can imagine implementing this in many different ways. But the way in which this one actually is implemented is as follows. So currently the boy, Marco here, has just one script. And as soon as that green flag is clicked, he's going to forever wait until he hears the spacebar pressed. And as soon as he hears the spacebar pressed, he himself is going to visually say Marco for 2 seconds, just so that we have some interesting aesthetics. But then he's going to use this broadcast puzzle piece. And you can hard code into this part of the puzzle piece any word that you want just by choosing new. So you can broadcast, that is, trigger multiple events for more complicated programs. In this case, I'm just broadcasting something I very generically called event. But meanwhile, look at the girl's script. She does not begin execution when that green flag is clicked, but rather only when she receives that particular event. So this, too, is another way that threads, or in this case sprites, can intercommunicate, but by way of this broader construct, if you will, known as event handling. So now let's come back to Oscar time for a moment. Oscar time manifests now, 2 years later, an interesting bug, which we'll rather conclude on or touch upon briefly today, related to precisely those topics we were talking about a moment ago, threads and this inter-process communication. But consider for the moment the following aspects of Oscar time. So in that game, there were several different components. And again, as always, you have cheat sheets in front of you. But try to recall, after the instructions were played, what happened in the program when Lauren started, or when Daniel started playing. Sorry? OK, so trash started falling. All right, so based on what you know about Scratch, how was the falling of trash implemented, do you think? Sorry? All right, so presumably, just to back up, we had a sprite, and it looked like a piece of trash. I added like a GIF that looked like a piece of trash as its costume. And then I had to choose some coordinates for it. Maybe it started somewhere at the top of the screen. And then what did presumably that piece of trash do in a loop, cyclically? Yeah, just decrease its y coordinate and just move down 1 pixel, 2 pixels, 3 pixels, and so forth. Those other pieces of trash probably were implemented identically, right? They had different costumes. One was an umbrella, one was a clock. But they, too, all started in the same fashion. But the program was at least somewhat interesting in that the trash, if you looked carefully, didn't all start from, say, the same point in the screen. Otherwise, Daniel could have simply gone back and forth to that same point. Rather, what was happening as the trash fell each different time? Yeah, it had a random x coordinate. And we saw on Wednesday that Scratch does have this capability for generation of pseudo-random numbers. And that's another sort of general idea that we'll revisit in this course. And you can spend practically weeks in some of the higher level math and computer science courses as to how to truly generate random numbers given a deterministic device. But for now, we'll simply take for granted that you can generate random values. Well, what else happened in Oscar time? So a piece of trash fell. And what was obviously the goal of this game? All right, so to collect the trash. So you know that Scratch has this ability to detect if the cursor, the mouse, is over a piece of trash. So just what kind of construct was probably used to detect whether or not Daniel's mouse was over a piece of trash? Yeah, the if, right? The if block, right? Sort of very common sense deployment of some of those basic constructs. So let's take a look just briefly at how this thing was indeed implemented. This first phase, so this is a little screenshot at the left. How were the instructions implemented? Well, in a pretty simple fashion, show what is a costume, a picture, for 4 seconds, and then hide yourself. And the purpose of this, again, is not so that you know how Oscar time works, because that fundamentally is quite irrelevant after today's purposes, but rather to begin to think about and to look at more complicated programs in a sort of decomposing manner, to look at something that on first glance is fairly dynamic and complicated, and try just mentally to begin breaking these things up into their basic components. So dragging, how might we have gone about implementing something like this? Well, apparently, I use some kinds of events, which I'll wave my hands at for now. But forever, while the piece of trash is falling, I simply was constantly checking. If the mouse is down, what do I want the sprite to do? Well, Scratch has this ability to move the sprite to wherever the mouse cursor is. The idea being, as soon as I click on it, and it detects as much, and I start moving my mouse, the sprite is simply going to follow where the mouse is until I actually let go, when that Boolean expression then becomes false. And then it looks like I'm using some variables, good click and my click, to just remember whether or not I have clicked on this piece of trash before. But the details we'll wave our hands at. Well, what about the overarching game? How did I ensure that this game only lasted as long as the music? Well, I just played in Winamp or iTunes the actual song that I downloaded from somewhere. And I knew it was like, what, 90 or 134 seconds, give or take. It's a lot longer when you think about it, that game. So that's how long that game actually went on for. So how do you impose sort of an overall structure for your game? Well, one of my sprites, the Oscar sprite, simply had this thing, which is granted becoming a little unwieldy, but at least that's all the sprite was doing some stuff, waiting, doing some stuff, and waiting, while meanwhile, presumably, other sprites were actually doing the interesting work, where he was really just in charge. In particular, notice that the last building block there is stop all, and that's what governed when all of the other sprites themselves stopped. So that's another form of this inter-thread communication. Keeping score. So clearly, there's a variable involved in keeping score. But this ultimately is about animation. So this was another script in this Oscar sprite. Clearly, if you want to report what the current score is, I had to create this animation of Oscar popping out of his trash can. And the way by which I implemented that in Scratch was just to keep slapping different costumes on him, which were just different versions of the picture. So sort of like a cartoon storybook, like a flip book. He, too, just sort of rose out of his trash can just by presenting different images. Well, and finally, there's this thing, raising Oscar's lid. Well, there's also this capability in Scratch of detecting how close you are to, say, the mouse cursor or to, say, another sprite. So if you recall, when Daniel was dragging the trash toward Oscar's trash can, what was happening? Yeah, so the lid was popping open, which was just a simple change of costume, so to speak, pictures in the game. But it was doing that just by using this really big Boolean expression, checking if the distance for the from the sprite is less than 40 pixels from the trash, or less than 40 pixels from the sneaker, or less than 40 pixels from the newspaper. In other words, if any of those sprites that were falling were within 40 pixels of the trash can, its lid should go up. Quite as simple as that. So again, the lessons here are not how Oscar time is implemented, but to begin to think about things in the reverse direction. That is to say, we've been looking thus far at these programs in this decomposing form. We've given you a number of examples, and then we've considered, how does this thing work? Well, obviously, for problem set 0, you're going to be taking the other approach, probably starting from nothing and trying to create something out of that, and perhaps a fairly complicated vision that at first, for some of you who've never programmed before, might seem a bit daunting. So how do you go about implementing these things? Well, mentally do what we've been doing here verbally in reverse. Think about the program you want to implement, the game you want to implement, the animation, and think about what some of its basic building blocks are, some of the basic features. Don't try to implement everything at once, but just bite off, take baby steps, if you will, toward actualization of that idea. And let's go ahead and try to apply this for a moment. If I go ahead and open Scratch, click New, just to give me a blank, clean slate here. Suppose all I wanted to do was implement the falling of trash. Well, what I might do is say the following. When you create a new document in Scratch, you get a default sprite. And just because I already have that sprite there, we're just going to make cats fall from the ceiling rather than pieces of trash. So how do I go about using the puzzle pieces, all of which I think we've seen before, go about making this cat start at the top of the screen and start falling down? What do I do? Where do I begin? All right, so I can move it to the top of the screen. And just in real terms, most of your scripts will generally start with this kind of block, right? As soon as the green flag is clicked, commence. So the first thing I probably want to do is move that sprite to the top of the screen, and perhaps maybe somewhere along the XY axis. Well, how do you do that? Well, where do we go about choosing directions? Well, there's many ways to implement a lot of these things, but let's start with something simple. When the green flag is clicked, I want this sprite to go to x comma y. Well, what's the coordinate system? Well, you can kind of cheat, move your mouse over the stage here, and notice that 0, 0 looks like it's going to be roughly in the middle of the screen. If I scroll up, though, and I want to actually put this thing at the top of the screen, notice you have little hints there, mouse X and mouse Y. It looks like up here, the top of the screen is at 180 pixels. So I'm going to go ahead and say, all right, move the sprite to 180. And for simplicity, let's just leave it at X, X at 0. Let's go ahead and play this. All right, so didn't really accomplish all that much, but at least it's a step toward our goal. What's the next thing we want to do? Sorry? So we want to repeat something. So that's one of these control constructs. So let's forever do the following. What do I want to do? All right, so I want to move it down. And we've seen the move block before. We'll fit it right inside the forever construct. Change it just to say 2, so it moves slowly. I go ahead and click play. All right, so almost there. What clearly do we need to fix here? Yeah, so well, not just y, but really the direction. So there seems to be some kind of vector along which this thing moved. So let's actually fix this. Let's pull this out. And let's go ahead and say point him in the right direction first, which just from having done this before, I know is 180, is downward. So upward would be 0. So let's go ahead and piece this back together. Go ahead and click play. All right, and now we have the cat falling from the sky. But if we play this thing again, it's not quite a hard, challenging game if the trash always falls from the same point. So how do we quickly fix this? Yeah, so let's pick a random variable. That's under the numbers category here. So it looks like we can pick a random value. If I drag this over to the placeholder for the number, it'll pop into place. What number do I want to choose? Well, again, we can cheat. So the stage looks like it starts at -240 and goes over to +240. So let's say that. Start between -240, +240, click play. Now the cat's over there. Next, he's over there. Next, he's over there. All right, the code is right, though. There we go. All right. So it's working. Maybe not the best random number generator, but they're random, perhaps. Yeah. Good question. Can you change it so that he's falling feet first? You could. I think, though, the way you'd have to do that is to actually change the costume and rotate the costume 90 degrees, because there's two different concepts here. There's the orientation, the direction of the sprite, and what the costume just happens to look like. But although there are other suggestions. OK, so I'm about to be corrected big time. All right. Yes? Oh, you can make it glide. OK, so it turns out you can use the glide construct rather than move, and that will move it in an arbitrary direction. Yes? OK, good. Yeah? Left of the small icons. Oh, this here. OK, so actually, hit the square one. This one here. Hey, look at that. Very good. Kind of calls into question why I'm up here then, huh? All right. So excellent, class. We're progressing quickly. All right. So let's try, yeah, question.
So it looks like you're only choosing a random number once, and then it's forever moving 2 steps down, and then I don't know what Scratch does, but maybe it's looping it and just shifting it over in the X direction. Actually choosing a new number at random, so it's not in the loop.
Well, so to summarize, perhaps it's not choosing a new random number every time we execute it. It actually should be, because what we were actually doing, it wasn't looping per se. I was restarting the program. And in theory, it should be picking a different random number. And it is, just not perhaps as uniformly as you might expect over the range, -240 to 240. So let's try one more instance of building something simple, but again, starting from scratch, pun perhaps intended. So here we have a clean slate. We have our individual sprite. And suppose that we want to create sort of an annoying cat and mouse game, so to speak, but without actually the mouse. Rather, let's go ahead and do this. So I'm going to start and say, all right, first what I want this to do is to, let's say the following. Forever, I want this cat to try to avoid my mouse pointer. So the goal of this game, let's say, is going to be for me to try to click on the cat. But every time I get close to the cat, I want him to try to skirt away. So it is sort of a cat and mouse game, although for poor choice of explanation here, I'm the cat and the cat's the mouse. So how do we do this? Well, we know from Oscar time, for one, that there is this ability to detect just how close, say, the mouse pointer is, or even another sprite, to another sprite. So what I probably constantly want to be doing is something like this. So if, and this is under the sensing portion, so if the distance to, let's get this, rather. OK, so actually let's use this. So notice, not clicking in. So clearly there's a problem here, but where am I clearly going astray? What do I really want to put in this block? Yeah, so this is one of those Boolean expressions. It's not meaningful to actually just put a number there. Rather, you want to put some kind of Boolean test. So if we do go up to numbers and say something like, all right, well, if x is less than y, plug this in. But now we'll actually let that guy go there, choose from the drop down the mouse pointer. And let's say if the cat is, say, less than 40 pixels from the mouse, that's going to be worrisomely close enough that I want the cat to then move. So if the cat is within 40 pixels of the cursor, or equivalently, the cursor is within 40 pixels of the cat, what do I want to do to get away? Well, maybe let's, we know there's this go to command, so we can go somewhere. It'd be kind of a silly game if the cat always went to a certain point. So let's, again, use some random numbers there. So let's have him go to a random x, which we said could be -240 to +240, and then a random y, which, again, will be a randomly generated number. Let's slide this over to make room. So pick a random number. This time the range is going to be what again? Yeah, -180 to +180. Scroll back here. And so now every time I get close to this thing, hopefully it should be moving. OK, and it's jumping around. Now, granted, there's a probability that he's going to jump right to where I am, because we've seen the numbers themselves aren't very well randomly generated. And even if they are, there's still a chance, if low, that he might get there. But let's make it slightly more interesting. Suppose I actually do catch the cat, so to speak, and click on him. So I want to check not only, I want the cat not only checking if I'm close to him, and thus he should jump away, but if by some chance I do get close enough to actually click on him, I want something interesting to happen. Well, let's go ahead and plan for this. Let's pull this out, go back here, because now I want to sort of detect two things. If the cat is that close, or if I'm actually clicking on him, I want to do the following. So I'm going to steal this code and move it back up in here. So that behavior is going to be the same. But in other words, if it's not true that the distance is less than 40, but rather, let's see, else if distance less than 40, is this going to work? That's not the best way to do this. So how do we want to go about doing this? If the goal is to check, sometimes if the distance is less than 40 pixels, we want him to hop away. But if by chance we actually click on him, what do we want to do? All right, so we can use another if. So actually, let's go back to this approach. So pull this if up here and sort of go back to the way we were. So we could just do something that's not exclusive and just have them both checked. So if I pull this if up here, and how do I, whoops, we want it to go underneath. So how do I check if we've actually clicked on him? So if what? If the cursor's touching the cat and the mouse is down, so that sort of calls for one of these. sort of a Boolean and. We need both things to be true. So if we're touching the cat, the sprite, or rather, it's touching the mouse pointer, and what else is true? Well, there's this other thing we can detect. Well, if the mouse is down, well, what might we want to do? Well, here we can be maybe a little silly. So if we go to the sounds, let's say play sound. All right, so this is not a terribly interesting sound. The meow quickly gets annoying. What else can we do? Well, these are the sounds that are by default imported. That's the pop. That gets annoying. Well, what can we do? Well, turns out Scratch comes with some fun. Let's go through these real quick and find one. Not really relevant. Well, OK, probably not relevant either. OK. This one's actually kind of fun. How about that one? So you can actually just see the MIT grad students recording these things for the kids, I think. All right, so let's go with that one. Go back to scripts. So we're going to play the sound not meow, but scream. And let's see if we got this right. If you want, incidentally, to get rid of puzzle pieces, just drag them over, and they go away. Let's play this thing now. All right, so I'm following, but I haven't clicked. If I try to click, well, it's still kind of hard to get there. So this is when you can kind of do the cheat. Let's make the... I changed this now from, what, 40 to 1. So now I can get pretty darn close. So again, the takeaway here, besides just giving you another little taste of what's sort of fun about Scratch and what you can do with it, is that that's sort of the mindset with which you can begin to build your own program. Set out with a vision in mind, and then take these sort of baby steps toward it. Don't try to implement your whole program at once, because if nothing else, you're going to start to trip over, say, bugs that you didn't anticipate, or you're going to realize that the thing just doesn't work. And then figuring out among dozens of puzzle pieces why it's not working is a much more arduous task than actually focusing on the smaller pieces from the get-go. Yeah?
How would you change the sprite like you changed Oscar's image?
How do you change?
The sprite that you have?
Good question.
You can't like export it and then re-import it after it's
Change the... OK, so let me answer that in a few ways regarding costumes. So Scratch comes with a bunch of costumes. Among them is this picture of a cat. You can import GIFs and, I think, JPEGs and PNGs as well if you download them from the internet. It also comes with a built-in paint editor, so to speak. If I click Costumes here, just as a sync preview, and click Edit, you get this sort of interface with which you can just sort of make your own bitmapped art. The way by which, though, I made the Oscar time thing was essentially to take one image of Oscar, or multiple images from the web, import them as individual costumes, and just make sure they all lined up. And then I just kept changing the sprite's costume by going to the looks category here, and then you, quote unquote, switch to costume X, Y, Z, and that creates the illusion that the sprite is changing appearance because it's just putting new images on top of him. Other questions? OK, so we promised to point out this perhaps subtle problem with Oscar time. Those of you who have perhaps taken AP Computer Science before, or aspiring hackers, so to speak, might find this an interesting thought question after this particular comment. So Oscar time used to work perfectly, I would put forth. So 2 years ago, it worked great when Scratch 1.0 came out. And the complexity of this script essentially is designed to ensure that when Daniel, for instance, is playing Oscar time, if he clicks on a piece of trash, he only picks up one piece of trash falling from the sky at once. Even if by chance of the pseudo-random number generator, two pieces of trash, like the trash and, say, the umbrella, happen to be on top of each other, well, this code looks complex because it was designed to try to detect if the mouse cursor was over multiple sprites at once. In version 1.0 then of Scratch, when I played Oscar time, this code worked. In other words, this use of those variables I waved my hands at last time called myClick and goodClick were essentially this kind of shared memory that I used so that different sprites could detect if someone else was already clicked on. The idea being just this. If the trash sprite were clicked on, But the umbrella sprite were also clicked on. By checking the value of this variable, the idea was that the umbrella would check, hey, has someone else already been clicked on at this given moment of time? If so, I'm not going to, the umbrella, follow the user's mouse cursor. And in that way, were you able to detect whether or not multiple sprites were in fact touching the mouse cursor. Unfortunately, fast forward a year or two, when MIT released Oscar Time 1.1, now there's a bug whereby if you play this game and two pieces of trash happen to be floating on top of each other and you click one of them, both of them stick, so to speak, to the mouse cursor and they both get dragged. Now, I could spin that as a feature, right? It's just more efficient to be able to pick up multiple pieces of trash at once. But then it calls into question why there's this complexity for making trash fall. So the thought question I would put forth to those of you who are inclined to think this through is what might have changed about the implementation of Scratch, the program itself, that broke Oscar Time in this way. In other words, why, despite my use of shared memory, my click and good click, the particular use of which I'll let you try to infer by looking over the source code, was designed to prevent, why does that code no longer work? Why can someone pick up multiple pieces of trash? All right, let's field this now.
Maybe because the program's designed now to act as if things, like if you clicked on two things at once, it pretends that it happens simultaneously, even if it has to process one and then the other.
So that's the right idea. So it sounds like Scratch is just assuming if something happens now with two sprites, it really is happening simultaneously. Right, within a narrow enough slice of time, perhaps Scratch itself is assuming that that is considered simultaneous. So that's essentially the right idea. And the buzzwords I'll toss out if you want to sort of do some at-home research on this is Google terms like race condition and scheduling and CPU. Those kinds of issues which, to be honest, only tend to come up in, say, Computer Science 161. The operating systems course is very much at play here as to why the code is now broken. Something changed with regard to Scratch along those lines. All right, so the big question, who cares? So we've spent 2 days on Scratch. Well, what's the point? Well, again, the takeaway is to familiarize you with these basic fundamental constructs, which we'll be using throughout the term and are, of course, laced throughout programming itself. What's the next step we're going to take? Well, come Monday, our programs are no longer going to look like this at top right, but they're going to look more like this at bottom left. And again, I'll promise that some of you will bang your heads against the wall at some point because you've missed a parenthesis and you've missed a semicolon. And to be honest, as is the case when I learned programming and when these guys learn programming, sometimes you will stare at your own code for 5 minutes, 10 minutes, 30 minutes. Then you'll finally go to office hours, and in 5 seconds, a classmate or one of your teaching fellows will just say, well, did you close the statement with a semicolon? And bam, you'll never make that mistake again. But odds are you'll make that mistake once. The point here, though, is to say that what's going to look a little more arcane, dare say scary, on Monday is really just another implementation of the same ideas. Hello world at top right is simply going to become something a little more arcane looking like this. Statements that look like hello world at the top are just going to become a little more arcane like this at the bottom. But again, we saw this on Monday. Clearly, that's just a statement designed to print to the person's screen, hello world. Boolean expressions that look in Scratch like this are going to look a little uglier in text, but they're simply going to look like that. Conditions, which at left might look like that, checking if x is less than y. Well, that's just going to become this, written in text, which again, on first glance, might have seemed a little overwhelming. Certainly, if you're unfamiliar with this world, it might look like the proverbial Greek to you. But it's just another incarnation of these same ideas. Loops as well. Saying hello forever goes like that in Scratch. And the language we'll know as C, it's going to look more something like that. Same thing for repeating something 10 times in Scratch, looks like that. In C, it's simply going to look like that. So there'll be some new syntax to be sure, but ultimately it's going to be the same ideas. Variables, finally, that look like this in orange are simply going to look like this as integers at right. So that's enough fun for today. We will see you on Monday. Good luck with your projects.